Welcome back to our ongoing exploration of number theory. Today's deep dive takes us to a fascinating constant. The Lemniscate constant.
Oh, I like this one.
Right.
Yeah.
Think of it like pi's intriguing cousin.
Yeah.
But instead of circles, we're venturing into the world of the Bernoulli Lemniscate.
And, the more we explore this constant, the more we uncover these intricate connections to other mathematical concepts. It's like a hidden doorway to a whole network of ideas.
Okay, let's unpack this.
Okay.
What exactly is the Lemniscate constant? I feel like we need a solid starting point before we dive into all those connections you're talking about.
Absolutely. Just like pi is the ratio of a circle's circumference to its diameter. The Lemniscate constant is the ratio of a Bernoulli lemniscate's perimeter to its diameter.
So we're talking about a specific shape here, the Bernoulli Lemniscate.
Yes.
Can you paint a picture for our listeners who might not be familiar with it?
Picture the infinity symbol, that figure 8 shape. That's essentially what a Bernoulli lemniscate looks like.
Okay.
And just like the circle has its special constant, pi, this lemniscate shape has its own special constant,
Interesting. So is it just a coincidence that both these shapes have their own unique constants? Or is there something deeper going on here?
That's the beauty of mathematics. Often what seems like coincidence turns out to be a hint at a deeper pattern.
Right.
And the lemniscate constant doesn't just define a shape, it's also what we call a transcendental number.
Okay, break that down for us.
Sure.
What does transcendental mean in this context?
It means can't be a solution to any polynomial equation with integer coefficients.
Okay.
Think of it this way. You can't get to by simply adding, subtracting, multiplying, or dividing whole numbers. It's a number that exists outside the realm of those basic operations, which already tells us it's a bit special.
So it's a bit of a rebel, this Lemniscate constant.
Yeah.
It plays by its own rules, but how do we even work with it if it's so difficult to pin down?
That's where mathematicians get creative.
Okay.
They've developed all sorts of clever methods to calculate and represent. And get this, as of 2024, over 1.2 trillion digits of it have been calculated.
Wow, 1.2 trillion digits.
Yeah.
What's the motivation behind calculating a constant to so many decimal places? Does it unlock any specific insights?
That's a great question. It's not just about breaking records.
Right.
Calculating digits of constants like can help test the limits of algorithms and computational power. It also sometimes reveals hidden patterns or connections that we wouldn't otherwise notice.
So it's like pushing the boundaries of what we know and what our computers can do. It's almost like exploring a new frontier in mathematics.
Exactly. And speaking of frontiers, how does this Lemniscate constant fit into the broader history of mathematical constants? It feels like we've got this whole family tree of important numbers, each with its own story.
I'm glad you brought that up. It seems like there's always a fascinating history behind these mathematical discoveries.
Absolutely.
Where do we even begin with the Lemniscate constant?
Well, we can't talk about mathematical constants without mentioning Gauss.
Right.
He was fascinated by a concept called the arithmetic-geometric mean.
Okay.
And he defined his own constant, denoted as g, which is equal to divided by pi.
Hold on. Gauss, the arithmetic-geometric mean, and our Lemniscate constant are all connected.
Yes.
What's the relationship there?
The arithmetic-geometric mean is a way of finding a sort of average between two numbers.
Okay.
But instead of a simple average, it involves repeatedly taking both the arithmetic and geometric means of the previous results.
Okay.
It might sound complicated, but it has some surprising connections to various mathematical concepts, including elliptic integrals, which, as we'll see, are intimately linked to the Lemniscate constant.
Okay.
And Gauss was one of the first to really delve into these connections.
So Gauss saw a link between this special type of average, the arithmetic-geometric mean, and the Lemniscate constant. That's pretty incredible. And I'm guessing this is just the tip of the iceberg when it comes to the Lemniscate constant's connections.
You guessed right.
Okay.
Mathematician John Todd later introduced two more Lemniscate constants, A and B, which are O2 and 2 respectively.
Right.
It shows just how much depth there is to this area of study.
Wow, so it's not just a single definition. It's got all these different facets and relationships. It sounds like the Lemniscate constant has been quite the celebrity in mathematical circles.
It has, and that's what makes it so intriguing. It pops up in various integral and series representations, linking it to a web of other mathematical concepts like elliptic integrals, beta and gamma functions, and even the Riemann zeta function.
Okay, we're definitely going to need to unpack some of this. The elliptic integrals, beta and gamma functions, the Riemann zeta function, those are some heavy hitters in mathematics.
They are.
It sounds like the Lemniscate constant is rubbing shoulders with the all-stars. But before we get lost in all those connections, can we take a step back and explore some of the visual aspects you mentioned? You said there are integral forms related to areas under curves.
Absolutely. One of the ways to understand the Lemniscate constants through integrals, which, as you know, are often used to calculate areas under curves. Some of the integral representations of are visually striking, almost like geometric interpretations of this otherwise abstract number.
That's fascinating. It's like the constant has a visual side.
Yeah.
A way of picturing it beyond just a string of digits. Can you give us an example of what one of these visual representations might look like?
Imagine a curve that gracefully slopes downwards, starting high on the y-axis, approaching the x-axis as it extends to the right. Now picture the area trapped between this curve and the x-axis. The Lemniscate constant can be represented as a specific portion of this area, revealing a connection between this abstract number and a tangible geometric shape.
I'm starting to see how this constant can be visualized. It's not just some abstract concept floating out there. It has these concrete connections to shapes and areas. Like we're taking something that seems purely theoretical and grounding it in the visual world.
Exactly. And these connections go beyond just areas. Remember how we talked about the beta and gamma functions? Those powerhouses of calculus?
You mentioned they generalize the concept of factorials to complex numbers.
Yes.
But how does that tie back to our Lemniscate constant?
Imagine you have a set of building blocks, but instead of being simple squares or rectangles, there are these intricate shapes that can be combined in countless ways to create complex structures. The beta and gamma functions are like the master builders in this scenario. And the Lemniscate constant is one of the unique and fascinating structures that can be created using these functions.
So it's like the beta and gamma functions are these versatile tools that can be used to construct a wide range of mathematical objects. And the Lemniscate constant is one of the beautiful and unexpected creations that emerge from this process.
That's a great way to think about it. And these connections extend even further, reaching into the realm of the Riemann zeta function, which is famous for its ties to prime numbers.
Okay, now we're really getting into the big leagues. The Riemann zeta function is one of those mathematical concepts.
It is.
That seems to be at the heart of so many mysteries. How does our Lemniscate constant fit into that picture?
The Riemann zeta function at its core is a way of adding up an infinite series of fractions. And believe it or not, there are certain values of this function that are intimately related to the Lemniscate constant. It's like these two seemingly separate areas of mathematics, prime numbers, and the geometry of the Lemniscate are secretly communicating with each other through this function.
That's mind-blowing. It's like discovering a hidden tunnel connecting two seemingly distant parts of a city. It makes you wonder how many other secret connections are out there in the world of mathematics, just waiting to be found.
Absolutely. And speaking of connections, we can't forget about series. This is where we see some truly elegant parallels between pi and the Lemniscate constant.
Series. Those infinite sums that seem to stretch on forever. I remember learning about some famous series for pi. Like Viète's formula and the Wallace product. Are you saying there are similar series for the Lemniscate constant?
Forget it. There's an analog of Viète's formula for It's almost identical in structure, just with slightly different operations. And the same goes for the Wallace product. It's like pi and the Lemniscate constant are reflected in each other through these series representations.
So it's not just a coincidence that they're both irrational and transcendental. There's this deeper structural similarity that's revealed through these series.
Exactly. And of course, we can't talk about series without mentioning Gauss. He developed an infinite series for divided by pi. A beautiful demonstration of how an infinite sum can converge to a specific constant.
It's always fascinating to see how these infinite processes can lead to precise, finite results. But I have to admit, I'm still struggling to grasp the intuition behind how that's even possible.
It's a head-scratcher for sure.
Sure.
Think of it like this.
Okay.
Each term in the infinite series gets progressively smaller and smaller.
Okay.
It's as if you're taking increasingly tiny steps. And even though you're taking an infinite number of steps, the size of each step shrinks so rapidly that you eventually converge to a specific point, a finite value.
Okay, that helps. It's like zooming in on a map. You can keep zooming in infinitely, but you're still confined to a finite area.
That's a great analogy. And speaking of zooming in and exploring further,
okay,
let's delve into continued fractions, which offer yet another fascinating perspective on the Lemniscate constant.
Continued fractions. Yeah. Those fractions within fractions that seem to go on forever.
Yeah.
They always seemed a bit mysterious to me. How do they connect to the Lemniscate constant, and how do they relate to the series representations we've been discussing?
Think of continued fractions as another way to break down a number. But instead of using decimals, we're using fractions nested within fractions.
Okay.
And just as we saw with those elegant series representations, continued fractions reveal a striking structural similarity between pi and the Lemniscate constant.
So it's like they're following a similar blueprint.
Yeah.
But with their own unique sets of numbers filling in the blanks.
Precisely. For instance, you have that classic continued fraction representation of pi, 3 plus 1 over 7 plus 1 over 15, and so on.
Right.
Well, the Lemniscate constant has a continued fraction that follows a remarkably similar pattern, just with a different sequence of numbers.
That's incredible. It really highlights how these constants, despite seeming so different on the surface, share these deep-seated structural similarities. It makes you wonder if there's some underlying mathematical reason for these connections.
That's one of the big questions that mathematicians are still grappling with.
Yeah.
It suggests there might be a hidden framework, a deeper level of understanding that governs these seemingly disparate constants and their relationships.
It's like we're seeing the shadows of a grander structure.
Yes.
Hints of a mathematical theory that could unify these concepts in a way we haven't yet fully grasped.
Exactly. And for those who are ready to venture even further down this rabbit hole, there's Bronsar's continued fraction.
Bronsar's continued fraction.
This one's a bit more intricate, but it beautifully ties together both pi and the Lemniscate constant, further emphasizing their interconnectedness.
It sounds like a mathematical treasure waiting to be explored.
It is. And it reinforces the idea that even in seemingly abstract concepts like continued fractions, there are these hidden connections and unexpected patterns waiting to be uncovered.
Yeah.
It's a testament to the beauty and interconnectedness of mathematics.
Well, I think we've given our listeners a pretty thorough and fascinating glimpse into the world of the Lemniscate constant. We've seen how it emerges from the geometry of a simple figure 8. How it connects to a surprising array of mathematical concepts, and how it even reveals hidden structural similarities with its more famous cousin pi. Any final thoughts to leave our listeners pondering?
I'd encourage everyone to explore this constant further. Don't be intimidated by the seemingly complex concepts surrounding it. Remember, at its heart, the Lemniscate constant is a reminder that mathematics is full of surprises, hidden connections, and endless opportunities for discovery. Who knows what other secrets lie hidden within this intriguing number?
Just waiting for someone with a curious mind to uncover them.
Beautifully said. And on that note, we'll wrap up this deep dive into the Lemniscate constant. Until next time,
yes,
keep exploring the fascinating world of number theory.